Greetings and welcome back. This is Feed Me with some good coax. And we're almost done with second to last. Now with any antenna system, the efficiency is going to rely on the antenna and your coax. A common use of coax cable is carrying RF signals between radio and antenna. Coaxial cable is more often than any other feed line for radio antenna systems due to its ease of use and requires special fuel installation considerations. So coax, you have coax and you have ladder line, and coax is going to be used more often in your radio station than ladder line because there's some advantages to it. Coax is very easy to bend. You can have it near metal, and there's no special installation requirements. So you can feed it pretty much through anything. And this is coax cable. So you got the shield, which is braided, and then you have the center conductor, and you have the center insulator and a jacket. And the center is called the dielectric. And there might be a foil shield in there. It depends on the coax. There's all sorts of different types of coax. The most common used coax in typical amateur radio installation is 50 ohm impedance. Okay, so there's some thicker coax. This is half-inch coax. I'm not sure what type it is, but it's probably either RG8 or similar. As the frequency of the signal passes through the coax cable is increased and the losses increase. So as the higher the frequency goes through the coax, loss starts increasing. PL259 type coax connectors are commonly used for HF frequencies. So they're only good for up to, I would say, about 200 to 300 megahertz. Anything from a couple megahertz on up to about 200 or 300. Anything beyond that, 200 megahertz higher than that, you want to use a type N connector. And it's more suited for higher frequencies. Let's see. The disadvantage of an air core coax cable when compared to a foam or solid dielectric type is that it requires special techniques to prevent water absorption. So this is what you would see on a tower system, and it's all hollow. It's kind of like a copper tube. And the reason why it's a copper tube is something called skin effect. As frequency starts increasing, you no longer need the center conductor of your conductor. It starts going to the outside wall of your conductor. So an easy way to get something very light is just to hollow it out, right? Because you're only using the skin of the conductor. You're not using the whole thing for RF when your frequency starts going up. And this is a inexpensive way to make some coax, because that center, if it was solid copper, wouldn't make a difference if it was solid or hollow, because it travels on the skin of the conductor or towards the outer edge. So with this technique, you need to put a inert gas in there. So it's a pressurized system. It's usually nitrogen that's pumped in here, and it's got to be totally sealed against the elements. I've seen many antenna installations on towers where you get a little leak, and this fills up just like a regular pipe would in your house, and destroys the coax. So a common cause for failure of coax cable is moisture contamination. So whenever you do any connectors connected to an antenna or to the outside, I always like to use some nice flexible electrical tape. It seems to work the best. Coax connectors exposed to the weather should be sealed against water intrusion and prevent the increase in feed line loss. The outer jacket of a coax cable should be resistant to ultraviolet light, which can damage the jacket and allow water to enter through the cable. So a lot of the coax now are UV resistant, and but if you don't have a UV resistant jacket and you have it exposed to the sun, it's going to crack, and that's how water can get in. Electrical difference exists between the smaller RG58 and the larger RG8 coax cable. it is that the RG8 has less loss at a given frequency. So the RG8 is the big thick half-inch stuff. The RG58 is the thinner quarter-inch stuff. So you would typically use RG8 in your base application, base station application. RG58 would be used in a mobile application. And there's actually better coax out there. I like to use LMR 400 Ultraflex. It's the same size as RG8 but less loss. And I like to use LMR 195 for wherever I'm going to put an RG58 equivalent in. Again, those other two coax I just mentioned are a lot less losses at higher frequencies than these guys. And this is a PL259 end right here. Okay, here's a chart of coax cable signal loss. So we have different type of coax. We mentioned RG8 and LMR 400. You can see the difference. If we're at 200 megahertz, RG8 has a loss of 5.4 decibels, and LMR 400 has 1.8 decibels. This is per 100 feet. So this chart's all for 100-foot lengths of coax. And you can see the different losses. As frequency goes up for any coax, the decibel loss starts increasing. So let's see, the lowest loss looks like LMR 400 in this chart. And just to show you guys, LMR 195, which isn't on that chart, but this is it. And it's a direct drop-in replacement for RG58. So this is what I use in my mobile applications, and it's a very, very low loss compared to RG58. And there's not really any special things you have to consider when installing these either. It's pretty much the same as RG58. So let's continue on. The lowest loss at VHF and UHF type of feed line is air-insulated hardline coax. So this is what they use on the towers if you're going over very long lengths. The instrument used to determine if an antenna is at resonant at the desired frequency is an antenna analyzer. So these are a couple of different antenna analyzers that are out on the market. These work very well. They're very small actually. They look bigger here, but they're about the size of 2 cigarette packs if you stack them side by side. And they'll measure your SWR, your impedance, anything like that. So these are pretty useful, handy tool. In general, the term standing wave ratio, SWR, is to measure how well a loaded match is to a transmission line. So that's all you're doing, is you're measuring the match. It has nothing to do with gain of the antenna. So it's just how well you are closest to 50 ohms for your impedance. Because you want to be at 50 ohms, you want to be at the maximum that you can transfer that RF power. So if you're mismatched, you don't get that efficiency. But if you're perfectly at 50 ohms or around 50 ohms somewhere, you get the maximum transfer of power. Okay, an inline SWR meter should be connected to a monitor the standing wave ratio of the station antenna system in series with the feed line between the transmitter and the antenna. So I like to do this once a year. Just throw my SWR meter on there and double check, make sure everything's in alignment. Make sure I don't have any water intrusion. You want to inspect your coax cables every year as well. Alright, so here's a typical HF station setup. You have your transmitter, you have the SWR meter, you have a automatic tuner, and then a low pass filter. So you have your SWR meter right here. It's important to have a low SWR in the antenna system that uses coax feed line to allow the efficient transfer of power and reduce losses. So here is a voltage of your transceiver, your voltage of your reflective, and your standing wave. So your standing wave is actually RF energy flying back into the transmitter. It's bouncing off the antenna and flying back. It's called standing waves. Okay, a reading of a 1-to-1 on SWR indicates that it's a perfect impedance match between the antenna and the feed line. Okay, so here's your SWR conditions. 1-to-1, perfectly matched. 1.5-to-1, good match. 2-to-1, fair match. 3-to-1, poor match. 4-to-1, something definitely wrong. Most of the modern transceivers that are out there now, once you get over 3-to-1, it automatically shuts off. The approximate SWR value above which the protection circuits in most solid-state transmitter begin to reduce transmitter is about 2-to-1. On my manual it says 3-to-1. So when you start getting too crazy out of whack, it'll actually shut itself down or reduce its power. Here's a meter indicating high SWR. With SWR reading of 4-to-1, this indicates that an impedance mismatch. Okay, some HF rigs have an SWR built in. This station shows a rig with an external SWR meter. This is a Bird wattmeter. And to measure SWR is you measure the reflective watts versus forward watts. And there's a little formula that you do to figure out SWR. So this is just a directional wattmeter. It doesn't do SWR automatically like some of the newer ones. This one you have to do manually. Okay, erratic changes to SWR readings might be caused to lose connection in the antenna or feed line. So it might be a loose connection somewhere. You want to make sure all your coax connectors are tightened, help minimize interference in erratic conditions. So the SO239 tends to back off with vibration. You just want to make sure everything's nice and snug. It's got to be finger tight. You don't have to crank it on too crazy. Let's see. A directional wattmeter is an instrument other than SWR meter that can be used to determine if the feed line and antenna are properly matched. So here's a single needle dual meter. So we have one needle measuring forward, one measuring reflected, and over here it gives you the SWR calculations. Power loss in a feed line is converted to heat. So if you have any type of high SWR, all you got to be doing with that power is converting it into heat into the coax. So that's not good. An antenna tuner matches an antenna system impedance of tuner transceiver to the output impedance. So while you have a manual tuner or an automatic tuner. Now again, this doesn't increase the efficiency of the antenna. It just matches the impedance. You can have a very poor antenna, and the auto tuner or manual tuner can tune it up, but you're not going to get very far because you have a mismatched antenna that's off a resonant. It just makes the radio happy. It makes the radio see 50 ohms. The primary purpose of a dummy load is to prevent the radiation signals when making a test. So a dummy load consists of a non-inductive resistor and a heat sink. So here's a couple of ones. Here's one in a paint can. This is a 1 kilowatt one, and this is a This is a dry type. This is a wet type. The wet type is filled usually with mineral oil, and here's the dry type here. It's just a carbon resistor that's in there. So if you're making tests, or if you're working on your equipment, you need to make some tests. Rather than radiate to an antenna, you can put it to a dummy load. And that's the end of that section. We're going to go on to the Q&A sections next.